Hi there, welcome to the Whistleput Classroom. Today we're going to talk about pitch, stability, and airspeed. If you go poking around on the internet or look in even some books on how to learn to fly, you'll find a story about what makes an airplane stable and how it relates to the airplane's speed. And the story goes something like this. Here's an airplane flying along, and it's got a wing like this and a tail like that, and as the airplane speeds up, there's more air blowing on the tail, which is at this angle, and it pitches the nose up. The Wright brothers actually wrote something like that. Other books will talk about the change of the downwash from the wing to the tail, causing it to pitch up as it speeds up and pitch down as it slows down. And of course, if you fly an airplane, or even fly a toy airplane or model glider, you know that if you throw it and it speeds up, the airplane tends to climb, and if the airplane slows down, it tends to descend. That's part of Glider 101. It's that you have to descend to maintain your speed. Or if you lose your speed, you have to descend in order to not fall onto the ground and maintain your level of flight. But that's not really quite what happens. So we're going to talk about what really does happen, and hopefully we can learn a little bit about how airplanes actually fly and build a better understanding of what's going on there. So to start out with, let's draw our usual picture of an airplane. And we're going to draw it reasonably large. And we'll give it a center of gravity. And it's got a wing. And because we showed that other thing, let's give it a tail at an angle. And the lift on the wing is going like this. And there's a lift on the tail. It might be going up, going down. We're just going to draw it up for the time being. And we can write down the equation for the lift on the wing. Lift is equal to 1/2 times the density of the air times the velocity through the air squared times the lift coefficient slope per degree of angle of attack times the angle of attack times the area of the lifting surface. So this could be S wing, this could be S tail, whatever. We also know that can quickly write down the moment or the torque caused by each of these lifting surfaces around the wing and the tail. And we're going to use a little bit of shorthand. We're going to call this Q. That's a typical term for this 1/2 rho v squared, so we don't have to write it over and over again. The moment due to the wing is just the lift times this distance. So it's Q times CL alpha times the wing size times this distance, and the moment due to the tail is Q times CL alpha times alpha, but the tail is at some angle we're going to call IT times the size of the tail times the length of the tail. And if we multiply out our algebra here, we get Q times CL alpha STLT, and Q times CL alpha IT, that's still an angle, times STLT. So those are the two moments that are caused by the airplane, the lift on the airplane's wing. And yes, in fact, we should probably be correcting for this angle so that these lengths are always constant, but we're going to pretend that this angle is small enough that change doesn't change very much. All right, what does that mean? Well, we know that in order for the airplane to be in equilibrium, that the moment trying to push the nose up has to be equal and opposite to the moment trying to push the nose down. So we'll just say the moment about the wing plus the moment about the tail has to be equal to 0, or the moment about the wing is equal to minus the moment about the tail. And if we plot this, moment wing and minus moment tail, we get something that looks like this. So we're going to put on the vertical axis moment, and on the horizontal axis we're going to put angle of attack. And this is 0. And we don't know any of these numbers. We do know from previous talking that we want the slope of the moment due to the tail to be steeper than the slope of the moment due to the wing. And we'll see why we need that to be true. We'll review that. So we're just going to pretend that if we multiply Q times CLL times S times LT together, that this is going to be equal to 2, so that the slope of this line with alpha will be 2, and for the wing we're going to pretend that it's 1. That's just going to make it easier to draw. Any real airplane, you know these real numbers, you get real moments. But for the purposes of these drawings, we're going to say the slope of the moment of the wing is 1, and the slope of the moment of the tail is 2. So we can draw the wing moment. We just look at this equation. We can see that when alpha is equal to 0, which is right here, this whole thing has to be 0. So we know that the equation has to go through 0, and we've said that the slope with alpha is equal to 1. So if we draw our line, it goes over 1 and up 1. That's a rise of 1 for a run of 1. And this is our moment due to the wing. And for the tail, we said that the slope is going to be 2 to 1, but we've got kind of two different parts of this. So when this part is 0, this part isn't 0 because these are all constants. There's no alpha in it. So we have to the equation has to go through this. And we're going to pick this to be a negative number because the tail is pointed down like this. IT is actually a negative number. So we're just going to call that minus 2. So there's our minus 2 point. So the line has to go through there. And we said that the slope of this line is going to be a slope of 2, which means it goes over 1 and up 1. And we're trying to get these nice and right because even though we're making up these numbers, they are numbers that have to be the numbers they say they are. And so this is the moment due to the tail. And you can see that they cross. So when the way we've written this, when this number is large, it means more nose down. And when this number is large, it means more nose up. So if the point where they cross is the trim point, because that's where they're equal, so there's as much nose down as there is nose up. And if the airplane increases its angle of attack, we get more nose down than we get nose up, so the airplane wants to pitch down. If the airplane decreases its angle of attack, we get more nose up than we get nose down, and the airplane wants to pitch up. So that's the basic review of stability. The question is, what happens when the speed changes? When the speed changes, this number gets a lot bigger. If it doubles, it gets 4 times as big. So that's going to change our slope because our slope is part Q. So in the next section, we'll talk a little bit about what happens to this graph when the speed increases. Thanks for checking in with the Whistle Pig Classroom. We hope you learned something. We hope you had a little fun, and we'll talk to you soon. Bye-bye.